Tonight, Mr. David Dana-Bashian will reprise the subject, 16 nearly impossible issues for evolutionists to answer, for the 8th time. The remarks are a series of brief sketches responding to 16 issues for which evolutionists in a broader sense have seen a stake and proposed various solutions. He will show that such attempts as they currently exist violate basic, well-known laws of mathematics, physics, and chemistry. Mr. Dana-Bashian holds a Bachelor of Science degree in mathematics, a Master of Science in mathematics, and a Bachelor of Science in chemistry, American Chemical Society certified, all from Purdue University. A former senior engineer scientist for the Boeing Company, he continues to serve as an aerospace consultant, following more than 20 years' experience in scientific programming and analysis, specializing in control systems. So without further ado, please welcome to the stage Mr. David Dana-Bashian.
Thank you very much, and thank you for attending. Tonight's talk is 16 Nearly Impossible Issues for Evolutionists to Answer. There is my email address should you care to use it. So the main objective is to sketch the 16 issues and then to show that evolutionists' responses, if they exist, fall short. You might recognize this quote from The Blind Man and the Elephant, especially the part saying, though each was partly in the right and all were in the wrong. 6 men, each with their various perspectives. Especially since we don't know a millionth of 1% about anything, according to Thomas Edison, who probably had more patents in this day than anybody else. Here are some preliminaries. There are 4 philosophical schools of thought that I learned about in History of American Education class. The absolutist school, which says somebody told you. The empirical school, which means somebody tested it. The pragmatic school, which means somebody found that something worked. And the existential, which is to say somebody found that something occurred. And of these schools, I'm going to select empirical for the purposes of this discussion. Verified scientific laws do not displace other verified scientific laws. So when somebody comes along and says, I found this newfangled law, ask, what about the ones that we already know are true? Or as Stephen Wolfram found out on February 1, 2003 at Caltech in front of his old alma mater and 3 skeptical professors, and I was there to see the talk, the new science better agree with the old science. It's hard enough to interpolate between points, that is, trying to fill points between. However, scientific endeavors going into the past are going into the unobservable, unrepeatable past by extrapolation, which is fraught with mischief. There are 3 laws of thermodynamics that you might be familiar with. The first one says you can't win, you can only break even. And the second law is you can only break even at absolute zero. And the third law is you can't reach absolute zero. And there's a 0th law, you must play the game. And so therefore the conclusion would be you must lose. Nothing intervened. I'm also going to use a generalized notion of evolution. Evolution, when we use the term, just simply means change. It applies to any number of categories, not just Darwin's theory of evolution, which will also have some part in this talk. In fact, somebody supplied to me 9 textbooks, at least the pictures thereof, that discuss cosmological evolution, to show that evolution also is held in regard in other areas, not just Darwin. And here are the 9. You can look at them later if you care to. There are many others, of course. So here are the 16 issues. Of course, that's too many to read at one time, so I'm going to go over them a little bit slower than that. First, in the area of cosmology, why does anything exist? Issue 2, did the universe always exist? I'll go over them slowly in more detail. Issue number 3, did the universe cause itself to exist? Issue number 4, how can the universe avoid heat death? Issue number 5, how can any material travel faster than the speed of light? These I grouped together in the cosmological section. In the physics and chemistry section, issue number 6, what is the origin, transportation, and distribution of carbon? A hardly covered topic. Issue number 7, how do any stars exist? Issue number 8, how do moons form? Issue number 9, what is the ongoing source of comets, particularly long-term comets? Issue number 10, how do any elements heavier than iron exist? Another hardly covered topic. Under the biochemistry, biology, and information section, issue number 11, how do peptide bonds exist? Issue number 12, how do proteins have only L, or left-handed amino acids? Issue number 13, what turned non-life into life? Issue number 14, how does metamorphosis occur? Issue number 15, how do major morphological changes occur? Issue number 16, what creates information from gibberish? Now, you may notice that that pretty much covers a panoply of topics. And I'll be issuing a brief sketch of one or perhaps a few aspects of those 16. We're essentially going from where the evolutionist, if you like, and I use the term broadly again, evolutionist, starts from whatever, a nothing, a singularity, all the way up to the present where we're dealing with the information age. In cosmology, why does anything exist? Well, if nothing exists, we don't have any space, material, people, meaning, we have nothing. And from nothing, nothing comes, it's been said. I would propose to you that Roget's pocket thesaurus is a good place to start, if anything. Roget's pocket thesaurus is a treasury of synonyms, but more than that, it's great for a structure of the language as well. Category number 1 is existence. It would stand to reason that if category number 1 is existence, that the latter categories might have something to do with the possible causes of existence. Also under the category of why does anything exist is why this particular amount of mass. It's been said that there are 10 to the 80th atoms in the universe. Why not 10 to the 79th? Why not 10 to the 81st? Why any particular number? And why the particular distribution that it has throughout the universe or in place particular in the universe, such as the Earth? Why does the amount of matter greatly overwhelm the amount of antimatter? These are questions that there are virtually no answers or even discussion on the other side. Now I want to say also a word about quantum fluctuations. That's the popularly held belief that nothing can turn into everything. Really? If nothing were to turn into a particle and an antiparticle, do they really come back together and form nothing again? No. If they were ever to collide with each other, they would annihilate each other and form energy. If we were to repeat that process endlessly, we could form endless amounts of energy out of nothing. That would be a violation of the first law of thermodynamics. That's not what's touted anyway. What's instead touted is that there's an already existing energy field out of which the particle and the antiparticle come, into which they can return. But that leaves unexplained why there is such an energy field and what its purpose would be, let alone what caused it to occur, if anything. Issue number 2, did the universe always exist? No. Otherwise, we wouldn't exist. Everything would have already dissipated an infinite time ago, according to the second law of thermodynamics, if it had always existed. Now, either the universe is open or closed. If it's open, this could allow the possibility of outside entities, say a god, to come in. On the other hand, if the universe is closed, then the thermodynamics are still there. The fate that I already described would still take hold. Issue number 3, did the universe cause itself to exist? Now, I've had people answer this question in the affirmative, just like they answered the other in the affirmative, never realizing that those two answers don't agree with each other. No. Otherwise, the universe would have had to have existed before it existed to cause itself to exist. Or, alternatively, it would have to existed and not existed at the same time in the same way. This is a logical contradiction either way. I can use these three issues to form a cosmological argument. The basis of 1, does the universe exist? Yes. 2, did the universe always exist? No. 3, did the universe cause itself to exist? No. Therefore, have the grand implication that the universe has no material cause, because every other possible cause is a subset thereof. That leaves me with only 2 possibilities. Either the universe has no cause, which is unscientific, it's an Eastern mystical discussion. It belongs really in the camp of existentialism, which I mentioned earlier. Or the cause must exist, but it must be immaterial. Now, choose from the following possible list of immaterial causes. Fairies, leprechauns, gnomes, my favorite, flying spaghetti monster, God. You add to the list, oh, by the way, only God even has any testimony. So when somebody tells me that my theory is no better than that of a flying spaghetti monster, I will turn to that individual kindly, hopefully, and say to him, I don't believe in flying spaghetti monster. You do. And I never get an argument at that point. I can also rearrange these blocks to form a waterfall chart. Issue 1 basis, does the universe exist? Yes, because, well, no would obviously be false. We're here. Does the universe have a cause? Yes. If not, it's unscientific. And is that cause material or immaterial? Well, if it's material, did the universe always exist? No, because otherwise it would violate the second law. Did the universe cause itself to exist? No, that violated logic. So the cause must be immaterial. We're back to the choices of immaterial that we saw earlier. This is powerful stuff. Issue number 4. How can the universe avoid heat death? Well, from the foregoing, it can't. The universe will eventually completely dissipate if nothing intervenes. And is there any other hope? Well, as I said earlier, the new science better agree with the old science, and the thermodynamics are still there. They're still acting. And for those people who think that things can order themselves in a small part of the universe and at the expense of the rest of the universe, I have a problem with that, and that is eventually the surroundings that order originally came from are going to dissipate back into the surroundings eventually over time. There's no way to avoid this matter to occur if nothing intervenes. 5th issue. How can any material travel faster than the speed of light? Well, you might have thought that there wasn't any way it could have, but for those who are proponents of the Big Bang in some form or another, they hold that there was a point in time, shortly after the beginning of the Big Bang, where the universe inflated, or as I call it, hyperinflated. Some say it's 10 to the minus 31 seconds. There are other variations. How would anybody know what time it would be, let alone how does anybody know that it really occurred? Why not some other time? 10 to the minus 32 seconds, 10 to the minus 30 seconds. Why only at one time instead of a series of times? And there's also a problem with the graceful exit. Now, somebody claimed to solve this one in 1982. That would be saying once it hyperinflated, it had to somehow gracefully exit that point so that it would be gradually tapering down into its normal inflation or normal expansion. Well, meanwhile, Hugh Ross's Reasons to Believe doesn't have any answers to these kinds of things, nor to the next issue. In the physics and chemistry section, what is the origin, transportation, distribution of carbon? Now, I'd like some help from the audience. What examples of carbon do you see or not see shown in this figure? One example at a time, please, from anybody in the audience. Anybody?
Coal.
Coal. There's one. What's another one?
Diamond.
Diamond is another one. What's another one?
Carbohydrates and plants.
Right, vegetation. Anything else?
Rocks. Calcium carbonate.
Calcium carbonate is an excellent possibility. Somebody gave it another talk. Yes. Another? Any others?
Carbon and smoke.
Getting close.
Carbon dioxide.
Carbon dioxide. Carbon dioxide. Anything else?
Carbon monoxide.
Carbon monoxide. Very good. Anything else? Cows.
Methane?
Methane, there we go. There are any number of compounds that have carbon in them. I'm not disputing the fact that they do, but I've got a question to ask. Where did the carbon come from in the first place? That supposedly was answered in the late 1940s, early 1950s. It involves something called the triple alpha process, which I'll describe in a moment. So the proposed action is that red giant stars, in some stage of their development, underwent triple alpha process to get over the ordinary hump that a book like this would describe, maybe not as well as it could, about the mass gaps 5 and 8. The suggested mechanism to get it here in the first place was a supernova, but how it distributed itself the way it has, we don't know. Let's see that carbon is located in the second row of the periodic table underneath the arrow listed. You can see that hydrogen is over on the left side and helium to the right. Ordinarily in a star, which we're going to cover in a moment, starts off with hydrogen, fuses to helium, and there it would end. We wouldn't get to lithium, beryllium, boron, or the rest of them because of the mass gaps. How to overcome the problem of getting to carbon then? This was the mechanism proposed. It's called the triple alpha process. 2 helium atoms, which had fused from hydrogen, combined to form beryllium-8. That's one of those mass gap points. And before it could dissipate, in 10 to the minus 15 seconds, another helium joins the fray to form the full complement of 12 for carbon. It can only be done at one nuclear resonance, only in red giant stars, and can be disseminated only by a supernova that occurs long after the red giant phase. I've got a problem. Won't a supernova blow everything out into all directions? How will any of it concentrate anywhere? And regarding the transportation just to the Earth, consider also that the carbon would have to dodge all the gravitational effects of all the heavenly bodies en route to the Earth, including all those gas giants, Jupiter, Saturn, Uranus, and Neptune, and all of their moons, and all the asteroids. That besides all the stars that would have to dodge en route just to get to the solar system as it would have existed. Mind you, that's never mind what form those planets would be, whether nebular or otherwise. And then once it reaches the Earth, that it's distributed such that there are miles deep, thousands of miles long, solid coal beds several places throughout the Earth. Yeah, that would give me pause too. Here, for example, is a chart showing the world's coal deposits. You can see how irregularly they are spaced. And where those are located, in some cases, is very unusual. Notice Siberia has a large one. So does Upper Canada. But nothing to be seen in the Amazon region or in Africa. And even where they do exist, notice that they are existing in concentrated spots. It's not as if there is a uniform distribution of it, which would not be economically mineable or viable. Now, to get any of this carbon, we have to answer issue number 7. How do any stars exist? Assume for the moment that we have a Big Bang, all the mass is inside that infinitesimal volume, and the Big Bang explodes and sends all these particles, whatever they are, in every direction. What will Newton's laws guarantee? The particles will keep moving away from each other, and moving, and moving, and never stop moving. And they're moving at quite a high velocity, too. What do we need to form a star? A compression of gases. We have a hard enough time trying to compress those gases here on the Earth. We need a compression device of a much smaller volume. The temperature goes from hot to cold, and once the compression device is removed, then the atoms that were the liquid or gas that the liquid or solid that the gas has now become, now turn back into gas and dissipate once again into their surroundings. This is anything but what has been touted to occur in the universe, where things go from cold to hot, in fact, much hotter than the Earth. How, in other words, to get those atoms to go anywhere near each other? let alone compressed to form a star. In fact, there shouldn't really be any stars using that logic. There is a flip side, however, and that is that if we assume a generous 20 billion years for the existence of the universe, and somewhere along the line somebody calculated that there were 10 to the 21st stars, how they came to that number I don't know, dividing that number of stars by the number of years says that we should have 50 billion stars produced every year on average. There was 50 billion stars for each and every one of those 20 billion years. Somehow I don't remember seeing any discussion in the news lately that we had met our 50 billion star quota last year. Now, it may be a much higher number in the past that goes down. It might be a smaller number comes up, but it still has to be 50 billion stars average. Seems to me that we get excited if we see even one star being produced. Issue number 8, how do moons form? In the case of the Earth, if something tries to impact the Earth, we'll take that case first, what's the most likely thing to occur? The object will just stay in the Earth. That's what happens to meteors all the time. Let's suppose that you had something that was big enough, traveling fast enough, and if it's going to the Pacific Ocean region, it better not be blasting out an ocean. Very well, no ocean in the Pacific Ocean region. What's it going to have to do to overcome the problems to get a moon? Well, first of all, the particles, if in fact they're coming up from the Earth, would most likely have to travel straight up, or else they'll have a greater chance of dissipating in the first place. All the while that they're traveling up, they are fragmenting because of tidal forces. And if they don't reach Roche's limit, which is about 1 to 2% away from the Earth, then they will come down in a shower of particles back to the Earth, and there goes your moon experiment. But let's suppose that they get beyond Roche's limit. Then they not only have to congeal and connect to each other, but they have to compactify with no known force for compactification. They also better not be traveling too fast, or else they'll reach escape velocity and then you'll never see them again. On the other hand, they can't be traveling too slow, because otherwise they'll come back to the Earth again anyway, congealed form or not. They'll also be fragmenting on the way down. Furthermore, besides reaching orbital velocity, there must be a tangential force perpendicular to the motion that must be imparted for an orbit to be achieved, with no known source of the tangential force. And those of us who have been in aerospace know the exacting conditions for an orbit. In the case of other heavenly bodies, let's say those gaseous giant planets I mentioned earlier, I have a silly question to ask. How do we get solid moons from gaseous planets by blasting the planet? And for those who think it's the nebular hypothesis, I have a different question, and that is, how did the gaseous giants become gaseous and their moons become solid? That way. And for those who want to entertain the capture theory, it's regarded by the scientists who are looking at it as being too coincidental. And also, if that's not enough of an argument, I have another question, that is, why is there no evidence of other tries? We have enough problems if a meteor comes in our direction. Remember that one a couple of years ago? Imagine what would happen if you saw a moon coming in your direction. So there are really no plausible theories currently. Here's an interesting statement from Wikipedia. Since tidal forces overwhelm the gravity that might hold the satellite together within the Roche limit, no large satellite can gravitationally coalesce out of smaller particles within that limit. Issue number 9. What is the ongoing source of comets? Now, we already have reasonable explanations, we believe, for short-term comets by the Kuiper belt, by the interplanetary disk, and we could perhaps say that those are adequate explanations for some of the long-term comets. It's the others that we don't have an adequate explanation for. By the way, short-term comets are 200 years or less in period, and long-term more than that. And for those other unexplained long-term comets, the Oort cloud was hypothesized, spelled O-O-R-T. What, might you ask, is an Oort cloud? It's an automatic pitcher of dirty snowballs, or whatever else comets are made of, conveniently, of course, to compensate for them losing their mass or falling into the sun or otherwise being lost. Any such Oort cloud, if it exists, would have to be far away, whether inside or outside the solar system, there is some hypothesis that says that there is enough attenuation in a particular part, and it's at the given distance for apogee of comets and such, but it's still a complaint that there's no actual evidence of an Oort cloud. Not one so that we could say, okay, there's the Oort cloud, and it's the body that's producing those long-term comets. And there is no other hypothesis that's been offered yet. Issue number 10. How do any elements heavier than iron exist? In the periodic table, iron is located in the 4th row, near the middle of the beige section, with manganese to the left and cobalt to the right. This graph is known as the average binding energy per nucleon curve. Notice iron, which is symbolized by chemical symbol Fe, and atomic weight 56 being its prevalent atomic weight. Notice that it is near the maximum of that curve. In fact, for all intents and purposes, is. To get to iron, the theory goes that we would have to have fusion. Notice, by the way, that there's some problems down there in helium around that, and shortly thereafter, remember that carbon problem I have? Now, what about trying to get elements beyond iron? Cobalt, nickel, copper, zinc, all the way up to uranium. You can only get them by fission, starting with uranium. So how do you get the elements there in the first place? Well, we have our favorite mechanism again, the supernova. The same one that gave us all that wonderful carbon dispersion. Well, I'm sorry, but I think that's going to also disperse all those other elements too, and make them not economically mineable or viable. So we also have a transportation and distribution problem as well with those elements. No matter whether we're talking about short-term or long-term processes, the RRS processes. You can check out my elementary modern physics textbook for more details on that subject. Here is a chart of the world's mineral deposits. You'll have to look at it a little bit closer afterwards, but if we were to look at it, we'd see that many of the precious materials exist in political hotspots such as South Africa, China, and Russia. In other words, the elements do not exist uniformly scattered. Otherwise, they would not be economically mineable or viable. And these are all elements for the most part, except for a few like diamond and aluminum, which are heavier than iron. Under the biochemistry, biology, and information section, I'm going to turn to now issue number 11, how do peptide bonds exist? I have in my hands models of amino acids. I'll get to the issue of one versus the other in a moment. Let me point out the salient features of one of them. This is said to be a nitrogen atom with 2 hydrogens associated. This forms what we call an amine group. You think of ammonia, would have a 3rd hydrogen. On the other side is a carbon doubly bonded to an oxygen, also singly bonded to an oxygen and a hydrogen. COOH, carboxylic acid. Base, acid. In the middle, a hydrogen atom and a functional group, which may be hydrogen or any of 19 other possible choices for a functional group. If we were going to be combining them, then we would form NHCHCO, NHCHCO, as you can see. If we don't have these bonds, we don't have proteins, we don't have enzymes, we don't have life, and as we all know, without biochemistry, it's amino world. Now, you can see in this particular figure that there are 2 amino acids up in the upper left-hand corner. In the leftmost, we see a hydroxyl group from the carboxylic acid. The hydrogen and the oxygen will combine with one of the hydrogens from the amine group and form a water molecule to form the peptide bond. Chaining them together, we form a protein. Proteins always chain together by peptide bonds in a linear fashion with no branching. Got a silly question. Have you ever heard that statement from Darwin that says, we came from a warm little pond? Just how is that going to occur? When a water molecule must drop out, not be absorbed by the amino acids? This is a problem. Okay, so there's no warm little pond. How they're going to find each other on dry land, I don't know. But let's suppose they do. We have two choices for the atmosphere above the dry land. It can either be oxidizing or reducing. If it is oxidizing, then the oxidizing agent will destroy the bond and maybe the amino acids. On the other hand, if the atmosphere is reducing, then there is no ozone layer and the UV rays come in and they destroy the bonds and maybe the amino acids along with them. Meaning, peptide bonds cannot form in the open for these three reasons. Instead, there have to be already existing structures inside an existing body to force the water out. This is an old chicken and the egg problem. By the way, which came first, the chicken or the egg? God. But of the two, a hen and a rooster came first. It wasn't Adam and Steve Rooster. It wasn't even Guinevere Hen. It was Adam and Eve Chicken. Issue number 12. Within those proteins, how come there are only left-handed amino acids? Now look at the figure very carefully and you'll see that those two are mirror images of each other. Let me also hold these up so that you can see them this way. Can you see in front of you and or on the screen that these two are mirror images of each other? Can you see that very carefully? Okay. However, I cannot stick one on top of the other and get them to match. They will not do so. They will disagree in two or more spots, like right there. It's not possible to get them to match because of the spatial geometry. Therefore, each one of the two is a distinct molecule from the other. Label one of them left and the other right. These molecules are sometimes called stereoisomers, enantiomers, chiral compounds, mirror image compounds. They all have more or less the same meaning. And these kinds of things can occur when there are four different entities surrounding carbon, as there would be for any non-trivial amino acids. Also for many inorganic compounds they exist. Now, the starting point for an evolutionist is always the same. Neutral ingredients, neutral environment, neutral energy source. And under those conditions, every experiment to date has shown that we get a 50-50 mixture of left-handed and right-handed amino acids in solution, with possibly some small variation for measurement, or if you introduce things like soil clays, you could get a 1% difference. You might be able to get more radical things than that if you have the Murchison meteorite, which hit Australia on September 27, 1969. But in any event, you will not get 100-0, which is what you require in this case. Isaac Asimov merely claimed that it just started off that way in one of his papers. If he had been here, I would have asked him, over the entire face of the globe, things do not replicate. That's the commonly held belief. Now, there are right-handed amino acids in other structures. The D, dextrorotatory. They exist in, for example, bacterial cell walls. They keep destructive enzymes, which are proteins, from attacking them. And by the way, if a bacterium ever encounters an amino acid that's right-handed, it will turn it into a left-handed and then digest it if it can digest it. Now, I'd like to read a sentence from page 236 of my Morrison and Boyd Organic Chemistry textbook to emphasize the point. If I can find the page. Sorry, 236. Indeed, we deal with optically active substances to an extent that we may not realize. We eat optically active bread and optically active meat, live in houses, wear clothes, and read books made of optically active cellulose. The proteins that make up our muscles and other tissues, the glycogen in our liver and in our blood, the enzymes and hormones that enable us to grow and that regulate our bodily processes, all these are optically active. Naturally occurring compounds are optically active because the enzymes that bring about their formation, and often the raw materials from which they are made, are themselves optically active. As to the origin of the optically active enzymes, we can only speculate. The situation is no better now than when this book was being printed in 1972, and the problem was known to exist more than 100 years before that. This is my biochemistry textbook from Lubert Stryer. It was within the first week of my biochemistry class that I came across this fact about amino acids being only left-handed in proteins. It took me no time at all to figure out that was going to be a problem for an evolutionist. And the only kinds of responses I ever got after that point, which I knew were going to occur, would be either dismissing the evidence for personal reasons or saying that molecules have minds of their own, which is, by the way, what the professor decided to say the next Monday. And I would say, what mechanism? And he never could come up with one. A little bit more about them. L versus D, that is, the left-handed versus the right-handed. They are usually thought to be counterparts to each other. Some people disagree with that, starting with elementary particles. I read a whole book on the subject, over 300 pages. I'm not convinced that that did it. It seemed like it was too long a trail that could go wrong. If you try to combine left-handed and right-handed together, it won't be favored. Geometry won't be right. However, there's no explanation for why you can't have an all right-handed chain.
What do you mean, not favored, L and D?
We'll answer questions at the end. This is a combined model with some wrapping around it. The central atom in this case will be the carbon atom, and either one of those sets of corners would show a tetrahedron inside a cube, embedded. I'd say that's probably no accident either. There are only 5 Platonic solids, and that's 2 of them. We can, in other words, use Euclidean geometry and calculate the bond angle for methane, which is the basis or starting point, if you like, for amino acids, as far as calculating the angle. And it'll show up as being the arc cosine of minus 1/3, which is approximately 109 degrees, 28 minutes, 16 seconds. If it's different from that, then we have some help in identifying our functional groups. This is an exercise, by the way, that could be done in high school, and I wish they would. We didn't see it until we were freshmen in college, but I know it can be done, and I wish they would. Issue number 13, what turned non-life into life? Suppose I start off with a dead dog. It's been dead long enough, 3-4 days. One small task, Hercules, breathe life into the dog. I've given you all that it has, its liver, its lungs, its heart, its spleen, its central nervous system, its gallbladder, its stomach. Just breathe life into it. What's the matter? Is this not a small task? Are you not Hercules? Well, maybe the problem is much bigger after all. So, if we cannot breathe life into a dead dog, what makes us think that we can breathe life into materials made into a dead dog? Of course, we have far less than that to work with if all we had is hydrogen. Or maybe just the infinitesimal from the Big Bang. There is no spontaneous generation. There is no Goldschmidt-Hopfel monster. And no, RNA doesn't do all the work. That's still a hypothesis. Life only comes from life. That's all we've ever known, whether from Pasteur or others. Issue number 14. How does metamorphosis occur? There are two different kinds. One of them is amphibian, the other is insect. I'll be covering one aspect of insect. Here's a chart showing typical metamorphosis cycle. The adult lays eggs, the eggs hatch into larvae, the larvae spin a cocoon or chrysalis around it to form a pupa, and the pupa emerges to form the adult. I'll even give you every stage except the pupa going to adult. Just give you that, even though we'd have to explain those too. How does a pupa, in its mushy state, with no control over its own destiny, turn into an adult? The young Earth creationists, the old Earth creationists, and the evolutionists have all within the last 5 years conceded the problem as a mystery. In print. I have the quotes. Now this.
We might want to look at metamorphosis. Most insects, about 87%, undergo a complete metamorphosis. That is, a larva, such as a caterpillar, builds a cocoon or chrysalis around itself. Its body inside then disintegrates into a thick pulp-like liquid. Days, weeks, or months later, the adult insect emerges, one that is dramatically different, amazingly capable, and often beautiful, such as a butterfly. The food, habitat, and behavior of the larva are so different from those of the adult, it's hard to imagine. What mutations could improve a larva? Certainly none that destroyed its nerves, muscles, eyes, brain, and most other organs, as occurs within the cocoon. So even if the larva improved, it later ends up as mush. From the evolutionary standpoint, liquefying complex organs is a giant step in the wrong direction. Millions of changes inside the thick liquid never produce something survivable or advantageous in the outside world until the adult completely forms. How did the genetic material for both larva and adult develop? Which came first, the larva or the adult? What mutations could transform a crawling larva into a flying monarch butterfly that can accurately navigate 3,000 miles using a brain the size of a head of a pin? Indeed, why should a larva evolve in the first place? Because it can't reproduce.
There's one person in this room who could replicate those statements. He's sitting back there. Dr. David Lehman. Issue number 15. How do major morphological changes occur? I have a chart showing some of the changes that would be required to go from fish to amphibian, from amphibian to reptile, from reptile to either bird or mammal, or if you want an alternative, from bird to mammal. You can see that in the first case we'd have to gain metamorphosis and we'd have to increase the heart chambers. The second, we'd have to lose the metamorphosis that we just gained, and you'd have to change the fertilization. The third, you'd have to go from cold-blooded to warm-blooded, from scales to feathers, or if going to a mammal, scales to hair. And you can see what the fourth would be. Not one of these changes has any reasonable hope of being explained by anybody. But I'm an empiricist. If you want to show me how that's done, go right ahead.
Well, never mind, evolutionists still insist that feathers evolved from reptile scales, specifically dinosaur scales, and to prove the point, they say that feathers and scales are so similar you can hardly tell them apart. Have you noticed that? One of the first people to say this was Gerhard Heilmann back in 1927. In his book, The Origin of Birds, he says the most striking peculiarity of birds is their plumage, which apparently has nothing at all in common with the scaly covering of reptiles. So much more surprising is it, on examining these structures in the microscope, to learn that the feather is nothing but a further development of the scale. Alfred Romer, very distinguished evolutionist, says birds have been called glorified reptiles. Feathers are in reality almost their only distinctive feature, and he says although these structures seem quite different from the horny scales that cover a reptile's body, the difference is in reality not very great. Well, you can look in your Encarta encyclopedia, if you have one on your computer, look up feathers and they will confidently declare that the feather is a horny outgrowth of skin peculiar to the bird, but similar in structure and origin to the scales of fish and reptiles. So I thought we'd do a little test. I had a laboratory technician that worked for me that had a pet boa constrictor. And I said, hey, the next time that little rascal sheds its skin, why don't you bring it on in and we'll look at it in the microscope, because I understand you can hardly tell a reptile scale from a feather. And so she did. She waited, and when this little rascal shed his skin, and by the way, I want to point out that no snakes were destroyed to do this study. We waited until they shed naturally. She brought the skin in, we put it under the microscope, and we magnified it. And this is what a boa constrictor scale looks like here. You can see the others around it. And as the evolutionists have told us, if you look at them in the microscope at least, they are remarkably similar to a feather. So then I took a picture of a feather, and I want you to see if you can tell the difference. So you may want to clean your glasses or something right now. If you got this one in mind, okay? If you get confused, just look at the top. It'll tell you which is which. Okay, that's the scale. This is a feather. What do you think? Should I go back and forth? You got it down, or... I mean, why do they say they're similar when they're absolutely not similar? In fact, I'll go further than that. They are totally different. Their mature structure is dissimilar, their function is dissimilar, their embryological development is dissimilar, their mechanism of growth is dissimilar, their mechanism of replacement is dissimilar, their chemical composition is dissimilar. And let's just look at the obvious. Scales are like folds in drapery, like drapery pleats. It's all one sheet. That's like when a reptile sheds scales. He doesn't shed them one at a time or two at a time, does he? The whole thing comes off as one sheet. In fact, reptiles typically have two layers, won't they? An outer layer and an under layer. When they shed the outer layer, then the under layer is exposed. Why do they do that, by the way? Why do they shed their skin? Because they're growing. Now, I want you to think about this. You get a box through the mail, and you're wondering what's in the box. You open up the box, you know what's in the box? A bigger box. So you shed the outer layer because the under layer is bigger. You got to think about that a while. Let's look at that boa constrictor skin. The tail's in the direction of the arrows. So to your upper right, that would be the tail. I don't know, 1/4 of a mile up there or something like that at this magnification. And you can see the scales are arranged in rows, sort of on the bias with the long axis of the snake. If we get a hold of the right side and flip it over like the page in a book, this is what the underside of the skin looks like. And so now the tail's in the direction to the upper left corner. And again, for those of you in the cheaper seats, let's magnify this a bit. This is where one scale just fit right underneath here. It fit right in there, so when the skin pulled off, that scale pulled right out of that pocket, like taking your hand out of a glove. And that's the way the scales are put together, is one continuous sheet. Now, feathers are completely different. Feathers grow out of follicles, just like hair. Hair grows out of a hair follicle. Feathers grow out of a feather follicle. But I'm here to tell you there's no such thing as a scale follicle. Now, what is a follicle as it relates to feathers and hair? It's a tube-like depression in the skin. You see it here. Goes down deep in the skin. All of the growth occurs in the bottom in what's called a growth collar. The feather grows out sort of looking like a thick hair. And when it comes out of to the surface of the skin, it all unfolds to make the feather. This is the way the feather follicle looks down in the skin. All of the growth is occurring here, and the feather's alive at this point, but as it makes all of its parts, it dies. It goes through a programmed cell death so that the feather that emerges from the skin is completely dead. This is how it all develops. Inside the shell here, we have what we call a pin feather. If you peel this shell away, you can see that this is the growth region at the bottom. The shaft goes up along the backside there, and then the barbs grow off this growth ring, and those little barbs get longer and longer. They grow from each side and meet at the other side. When the feather comes out of the follicle, this cylinder opens up, the barbs all swing down, and you get this big broad feather out of a hole in the skin that's not much bigger than a shaft. And that's the way each feather grows from living cells, goes through a programmed cell death, and rises up out of the follicle in that way.
Dr. David Minton. Before I go to the next topic, I'd like to read a small amount from a book called Flaws in the Theory of Evolution by Evan Shute, who was a prodigy. So we're going to find out. These are some of the comments that the editor, Charles H. Craig, made of Dr. Shute. Dr. Chute, a fellow of the Royal College of Surgeons of Canada, received both his undergraduate medical degrees from the University of Toronto. It is interesting to note that Dr. Chute was more or less of a child prodigy. Entering high school at 9 years of age, he matriculated at the University of Toronto at the age of 14, the recipient of a Carter Scholarship based on a record high score. Doogie Howser. An all-around athlete, he was intercollegiate light heavyweight boxing champion, a member of the wrestling and track teams, as well as of the college crew. Hulk Hogan, before his demise. He is a member of many international known societies, including the Canadian Physiological Society, the American Society for the Study of Fertility, the British Society of Endocrinology, the American Geriatric Society, an associate member of the Royal Society of Medicine, and a member of the Canadian Authors Association. He is listed in American Men of Science, American Men of Medicine, in the Canadian Who's Who's, and the Directory of Medical Specialists, and so forth. Now, yes, Dr. Chute is a lecturer of international renown, the author of numerous books of verse, and the editor of Summary and Annual Medical Journal. Does that sound like somebody who has an irrational view of the world? If you still think so, please let me know afterwards why you think so. Now, towards the end of chapter 2, mechanistic origins, which is most of what we were talking. Summary. Surely all these considerations illustrate the complexity of the problems and difficulties faced by the evolutionist and anyone who thinks that life arose of itself and ever since has developed on its own. One must remember at this juncture how many of these evolutionary suggestions used as arguments above are based upon the most tenuous possibilities, not probabilities, just possibilities, and how step after impossible step is begged in the course of these polemics, which are really nothing more in the nature of intellectual exercises than science. Because scientists enjoy playing such a game of chess, the game does not become truth. It is still just a crossword puzzle, or a problem like that of a sonneteer who undertakes to discuss the dictionary thoroughly in 14 lines, which must end in certain specified rhymes. A long succession of elaborate postulates such as we have listed in this chapter, and which are necessary, mind you, if an evolutionist is to be consistent in his survey of all of life, including its origins, is still science fiction. 1961 is when this book was written. It is still as true today as it was then. 16. Issue number 16. What creates information from gibberish? If you had a communication class, you might recall that we require a sender tuned to the receiver, a receiver tuned to the sender, and a medium that promotes rather than interferes with the communication. There are also measures that we can have to discuss how random or not random things appear to be, not merely whether they are. Among them are the autocorrelation function, which can be either periodic or aperiodic, and its glorification, the ambiguity function. If you want to bury a code in radar, such as you might see in this radar handbook by Skolnick, you do a lot of work in this sort of thing. There is also, meanwhile, a measure of entropy that's completely comparable to that which we saw in energy. They have, in fact, the same mathematical forms. Each of them does to the other, any more than the mechanical and the electrical equations are compatible forms of each other in their respective domains. From this book, Programming of Life, in the last chapter by Donald Johnson, the failure of purely physical theories to describe or explain information reflects Shannon's concept of entropy and his measure of news. Information is defined by its independence from physical determination. If it is determined, it is predictable and thus by definition not information. Yet Darwinian science seems to be reducing all nature to material causes. In other words, if all you have to start off with is randomness, that's all you'll end up with too, by definition. We need information. to communicate between DNA and proteins. The DNA cannot exist without the proteins, and the proteins without the DNA. Another chicken and egg problem. And there are many other such problems that exist as well. This is a picture of a later edition of Skolnick's Radar Handbook. By the way, I started off this talk with information, namely Roget's pocket thesaurus. This talk ends with information and thus closes the loop. Before I go on to Q&A, I'd like some help from the audience. You see 7 pictures of famous modern scientists. Would anybody like to state the name, the last name of any of those scientists? One at a time, please. Anybody at all?
Darwin.
No, Darwin's not in there. Anybody else?
Rahi.
Huh?
Kepler.
Kepler is which one?
The first one.
The first one on which row?
The top row.
Correct. 1 down, 6 to go. Any others? Yes.
Newton.
Newton would be which one?
Second from the upper left.
Second?
From the upper.
Yes, the top row, second from the left. Any others? 5 to go. They're all very famous. Yes?
Well, I believe the one on the upper right is Faraday.
The first row, the last picture to the right is indeed a picture of Faraday.
Now, the guy to his left might be Boston.
No. No. Any others?
Second row, last guy, Rutherford.
No. Not Rutherford. Any others? We have the third picture in the first row and all 3 pictures in the bottom row. Any other guesses here? Another? Yes?
I think Maxwell is the left one.
Maxwell, James Clerk Maxwell is indeed the one on the left in the second row. Any others?
Well, the middle one might be heavy set.
Middleman might be heavy set.
No, heavy side.
Heaviside, no, not. Any other? Yes.
Isaac Newton. Third one on the.
We already established Isaac Newton was the second one on the first row. Yes, okay. Any others? They're all very famous. Yes.
The third one on the top row is Linnaeus.
Linnaeus, indeed. In fact, it was said that he was supposedly more popular than Jesus. I don't know if I agree with that. All right? But that would be curious because Linnaeus himself would probably have been turning over in his grave to hear such a thing. Any others? We have 2 left. The bottom 2 in the middle and the right one in the bottom row. Any guesses about those 2? Put on your thinking caps. These, no, not Tesla. And these are more or less in chronological order, from left to right and from top to bottom. Think about your history of famous scientists going from past to present. Any other ideas?
Bell?
Huh?
Alexander Graham Bell?
No. Alexander Bell is not. Any others?
Mendeleev.
Mendeleev is not in there either.
Pasteur.
Which one?
The middle.
The middle one is indeed Louis Pasteur. Wow. Life only came from life. All right, and then we have the last one. That would be whom? Who, rather. Who would that be? Any ideas? Huh? Okay, if you go to your thermometer, think along those lines. Your thermometer.
Fahrenheit.
Nope.
No.
Lord Kelvin is correct. Lord Kelvin is correct. What else did these men have in common besides being famous scientists?
Christian.
They were not evolutionists. There were some who were back in those days, but not too many. In fact, they are among the 16 that I've listed here. These are all names that should look familiar to you, especially if you had any training in the sciences at all. And yet, without these 16 and others like them, we would have none of the modern conveniences or inventions, for the most part, that we have. Or it would have taken a much longer period of time to get them, more than likely. In other words, these are geniuses. We would be, let's just say, having a lot of hubris to think that we could go up against any of these people in their chosen domain in front of Alex Trebek's Jeopardy, whether that be single, double, or final. We have the gall to think that we were smarter than any of they. Instead, we're asking other questions about smart. Think of them. Here is a list of references that I have selected. They are all sitting here, for the most part. Only the ones in green would be considered on the creation side. All the others are either neutral or on the evolutionary camp. And there's nothing better than having your enemies testify on your behalf in the same direction. That's what makes them nice. Here's some credits I'd like to give. Tom Canfield is sitting to the back, as well as others. In. This time I'll entertain any questions, one at a time. Yes?
The L and D not favored, what was that? It was on 12?
Mm-hmm. That is, mixtures of L and D together are not favored. In other words, a left-handed amino acid followed by a right-handed.
Some kind of process that will either generate one or the other, by and large.
No, no, I'm saying to form linear chains of amino acids to form a protein, a left-handed amino acid followed by a right-handed amino acid is not favored compared to a left followed by a left or a right followed by a right.
Okay, so if you have a bunch of different ones and they hook together, they tend to hook together in the same correlate.
Well, if we get any proteins to form at all in living structures, they're only going to be left-handed to begin with.
But, you know, before we get to, okay, all proteins have to be left-handed?
They don't have to be, but they all are. And that's the key. The fact that they all are, even though that's not a definition of it.
In life they all are,
yes.
Even though it's potentially possible that somebody could go out there and make a right-handed protein just for the heck of it.
If you start off with neutral ingredients, neutral energy sources, in a neutral environment, you will get a 50-50 mixture of lefts and rights. Yeah. Sitting there in that warm little pond that you can't have anyway for other reasons. Namely, you can't get the bond to form in the first place between them. Right. But otherwise, it'll be a 50-50 mixture every time. In fact, we depend upon those principles in the chemistry laboratory every single time. Organic chemistry is terribly predictable, much more so than inorganic, by the way. We depend upon these kinds of things. In fact, if we're going to form pharmaceuticals, we better get the right ones. If we are going to form rubber compounds, we better get rubber instead of chucka, which is supposedly completely brittle and not useful for anything, even though it's just the mirror image. All right, any other questions? Yes?
You say that it's nearly impossible issues to answer. How about, what would they say to number 2 to combat your thesis there?
Well, I'm contending they don't really have answers, but I pose the questions anyway. They say that the universe did always exist. The problem, of course, is that we wouldn't be here if that were the case. Everything would have already dissipated according to the second law of thermodynamics. If it always, not merely a long period of time existed, but always existed.
And what if they say the way that it exists is in some sort of cyclical cosmology, and that in previous cycles a lot...
Yeah, that goes back to things like Roger Penrose's cycles of time. And of course, I've got silly little questions for people like him, and that is, however do you think that the last pop in a black hole is going to be the jumping off point for the next cycle when you still have thermodynamics operating the way it always did?
Well, some people would say, well, it begs the question to say that you still have the same laws in the prior cycle.
Well, whoever would say that they are different from what we experience now, is the burden of proof is for that individual to show evidence that they would be. And we have no such evidence at present. But of course, being empiricists, we always allow for the possibility of something else to show up. And by the way, that reminds me, we should be favoring the things that are more probable rather than the things that are the less probable. Right now, what we have is a variation on Carl Sagan. The impossible becomes the possible the plausible, the plausible, the probable, the certain. This is not science. Show me why the impossible becomes the possible and so forth before going on any farther. Otherwise, we're saying we believe in miracles over science. Any other questions? Yes.
Okay,
Take yours.
I'm not sure if it's true, but I read that in meteorites that they found, there's molecules that are out of the 50-50 left and right-hand proportion. If that's true, what would you guess the reason for that?
I don't have any. I mentioned the Murchison meteorite earlier in the talk. That's more or less what I was alluding to.
Okay.
There aren't any reasonable hypotheses for either, although some have speculated that maybe when they hit the ground they already became bacterially infected. How one would go about proving it one way or the other, I don't know. But the point is still that even with those vast differences from 50-50, it's still not 100-0, which is what counts. Nobody has even, I think, even gotten to the point of saying it's 70-30, let alone 100-0. So there's still a mountain to climb, even if the 70 could be explained. Another question over here?
Yes.
Yes.
I've always been a little puzzled by the, or other people that I talk to when I try to talk to them about information entropy. And you're saying that it has the same mathematical form as energy entropy, of course.
Mm-hmm.
Now, Poincaré said that if two theories have the same fundamental constant or the same mathematical form, that there's some more fundamental theory that's common to both, which both would be right. So, can you comment on the relationship between information entropy and energy entropy as far as physicality, or some more fundamental property? Or?
I wouldn't be able to assign a causal effect between the two any more than I'd be able to assign that between mechanical and electrical systems. Besides, I think that would be somewhat secondary to the point I'm making, and that is that the fact is that there is a correspondence between the two. And so what we see in one arena, we see essentially in the other. I wasn't trying to establish cause and effect between them, though.
Well, I've seen books and you have they say, well, 1 bit is equivalent to some small fraction of an erg or whatever.
Mm-hmm.
How do you feel about that? Do you feel that a bit of information is equivalent to energy?
I don't have anything to say at that point. Sorry. Anything else? Yes, another question?
Okay, I just want to know your thoughts on how cosmologists, create an estimate for the age of the universe, and if there's any value to that to you at all.
Well, I tend to think that they would have problems from the very beginning because, among other things, the more time you have, the less chance that quote-unquote evolution could ever occur because of the dissipation of things. Also, we have evidences of things that aren't that way, even though they weren't part of my talk, such as Niagara Falls. It's been said that Niagara Falls can't be more than 9,000 years old or so from its current flow rate, that is rubbing over the rocks. But generally speaking, I have enough fun with these issues, regardless of any others that they want to borrow more trouble with.
So pretty valueless to you for the most part?
Secondary.
Secondary?
Yes.
Okay, also, can you give me a really good definition and explanation of the word entropy?
Entropy is the measure of disorder. Yes. You can be specified as I have a couple of physical chemistry textbooks if you care to go into the line integral of delta Q over T, if that's of interest to you.
Thanks.
Yes, so the change in entropy. Yes, any other questions? Yes.
I saw something on the, you're talking about the Big Bang and everything blowing out, or it's uniformly in every which direction so it will never accumulate again, something along those lines.
Well, I'm saying that Newton's laws are still true, in which case the particles should be, in fact, expanding out from each other indefinitely. There should never be a collection of them again together, especially considering the speeds that they're supposedly going at as well.
So, 'cause I've seen arguments on that to the effect that you have all kinds of eddies that would go out there and, you know, it isn't going to distribute uniformly.
Yeah, well, I think that the person making those claims is the one responsible for showing the evidence for them.
Pardon me?
The one making the claims is the one responsible for showing the evidence for them, especially considering what we already know about basic dynamics, and that is that particles that move apart from each other just continue to do so. And the further apart they are from each other, the less possibility they ever have of coming together. And so forth and so on. That's my answer to a question like that. It remains to be seen. Again, being an empiricist, I would need to see the evidence in order to comment upon it.
Yeah, one of the guys said that you see this when you see an atomic bomb. Okay, yeah, basically all this type of stuff swirling around there. It does, you know, it's not uniformly distributed, is what I was saying.
Well, Big Bang processes, I understand, would be a lot more explosive than an atomic bomb as well. The particles are going at a much faster rate of speed than anything like that. And besides, even so, in an atomic bomb, we already have elements. Here we're dealing with things that aren't even that yet. They have yet to form any elements at all. Who knows what kind of particles these would be? But they're not elements yet. In fact, the theory is that you have nothing but hydrogen to begin with. Yes, Dave?
Forming the higher elements in the nucleus of certain stars, how does that, explain from the chemical standpoint, how does that actually happen? Of course, it's not something that we've seen empirically happen. So where did they come up with this idea, and how many seconds or fractions of a second does this occur in the...
Are we speaking about going from hydrogen to helium or something else?
No, not hydrogen to helium. We can understand that, but going to the heavier elements, we're talking about these stars. In the inner stuff, there's tri-alpha sort of combination. You gave a slide.
A triple alpha process.
Triple alpha process, yeah. And where did they come up with that?
Well, that was Mr. Fowler was one of the people that was responsible for that. There's another person who is, has a long Indian name, and Fred Hoyle was more or less the instigating scientist, although he did not share in the Nobel Prize, oddly enough, in 1983 that was awarded to the other two. So you can look up the Nobel Prize in Physics that was awarded in 1983 to find out more details about it. I don't think any of the participants is still alive. I think the others dissipated just a few years ago. But be that as it may, it was said to be, in some circles, the only example of the anthropic principle. That is, here we are, the carbon must have gotten here, this is a means of getting here, we don't know of any other means, that must be it then. It's essentially what it amounts to. Of course, I would argue that that has argument by incredulity buried in it.
Yeah, yeah.
Among other things, it doesn't really allow for the possibility that somebody could come along later and say, well, this is better, even though empirically we should allow for better explanations. Instead, we arrive at the prize and give it to them, and this is more or less sealed the fate so far of that mechanism as being the case. But it has a world of explanation that I think needs still to explain. And that's why I went into the discussion about the transportation and distribution issues, because those are not covered by any of the Nobel Prize, to the best of my knowledge. And again, I mentioned that Hugh Ross's Reasons to Believe doesn't either, even though they would be on board with us all. Anything else? Yes.
For the purposes of your video, some of your on-screen numbers are blocked off.
On this particular slide?
If you look,
Somebody's shoulder.
yeah, I don't know if it's a shoulder or a chin.
It's a shoulder.
Okay.
We'll take care of such things in post-production. At least, won't we?
Yes.
All right, anything else? All right. Well, if there are no other questions, then I want to thank you for your time and attention tonight.
I do have one more question, if you like.
Well, yeah, time's up.
For the filming purposes, probably time's up, but go ahead.
How about people like Lawrence Krauss who want to say that the cosmos came from nothing?
I just answered that question.
Yeah.
He doesn't have an answer for that sort of thing. Nobody does. Violates the first law of thermodynamics. Nobody is really touting that nothing turned into everything. That's the common misbelief. No matter whether it's Lawrence Krauss or who else is writing about it. Show me the evidence to the contrary. Then we can start talking.
Well, actually, he contradicts himself when he explains that is nothing has a bunch of stuff in it, which you never attempt to account for.
Well, then you've answered your own question, maybe.
I just wondered if you had a different...
No, I gave the answer that I gave earlier for the reasons I did. All right, anything else?
Yeah, I'm kind of curious how evolutionists react when you're interacting with them and you give them arguments like this.
I wish a few of them had been here, because I invited them.
They get angry.
They get angry?
Well, you can see some of the evidences of this in the CCCM version of my talk, October 19, 2013. Most of the questions, in fact, came from the agnostics, the atheists, and the skeptics. This is also evident in the quote-unquote debate that I had on June 17 last year in Villa Park, which is resident on the Backyard Skeptics site, is debate number 9, which is also available in the combined camera format, half of which was due to Dave Lehman's camera. And you can see traces of it elsewhere as well, but those are the most graphic examples I can think of. In fact, in one case, they tried to put words in my mouth in the third talk, and in about between minutes 9 and 10, I said, "Did I say anything like that?" And they admitted I hadn't, and I said, "Well, then I'll continue not saying anything like that." Yes, Dave.
If you want to hear what atheists say, Dave and I are going to be debating the atheists on the 24th of September, and that'll be in the 8101 Slater at the Huntington Beach Community Church.
Of the Nazarene, yes. Well, at least I'll be giving him moral support. I don't know how much more than that. All right? Yes?
Yeah, I was going to say, like, if they believe that God does not exist, but yet believe that evolution started the whole thing, I would think that it would have been impossible for evolution to even happen unless there's someone that starts it off, like a domino effect.
Well, they like to say that they can take care of the problems of getting to life and leave the evolution to us. Well, unfortunately, that leaves them unchallenged on the origins issues, which is why I continue to talk about them in a good chunk of the talk, no matter what their retorts seem to be online. And they tend to throw a lot of mud, unfortunately. It's not really a scientific discussion. It's instead a contest of wills. I'm not the slightest bit interested, by the way, in the contest of wills. I'm only interested in the truth, or at least the best approximations that we can give it within empiricism. And I also don't terribly appreciate it when they think that I have gone beyond the bounds of empiricism in any of the talks, like what happened at the pier last weekend. And I said, "No such thing, Mr. Thus and so." And I said to him, I can't prevent you from putting words in my mouth, but I can tell you that you're doing it. Leave it at that. Anything else? Yes?
You ever heard of the Origin of Life prize?
Oh, boy.
Somebody's actually put up $1 million for somebody who could come up with a plausible theory how life could have originated by natural causes.
Yeah.
It's been for 10 years.
Yeah, I imagine it probably will be for a few more, too. Yes.
I kind of, for some reason, kind of had a mental dropout at question number 5, how can matter move faster than the speed of light? And could you kind of just readdress that just a little? Because I really, for some reason,
I was covering the aspect having to do with what's called inflation or hyperinflation, as I like to call it, and that is that there is a specific point shortly after the beginning of a supposed Big Bang, 10 to the minus 35 or 31 or 30 seconds, whatever it is, where things suddenly went much, much faster and then came back down again. This is meant to try to overcome the problems of background radiation or background noise, if you like, or temperature being more or less uniform, more or less. Clumps, yes, but more or less uniform across the entire face of the universe as we know it. How could it have transmitted its heat across the entire universe without enough time to do so? Well, the answer supposedly is, well, we'll just have this kludge. It's like trying to get a perfect score on a test where all you have to do is take your answer, multiply by 0, and add the right answer. I wish I had those kinds I wish I had those kinds of things available to me when I was taking tests. I didn't. Yes.
Do you like the fine-tuning argument at all, or do you use it, or do you not like it?
I'll leave that for somebody else. I have enough trouble with the coarse arguments. Yeah. Anything else? No? Okay.
Thank you very much.
Thanks a lot.
We got 3 applause lines in the argument. Sorry, in the debate too.